All right. Good morning, good afternoon, good evening to all of you who are joining in the stream. Uh, First of all, very happy to be here. This is the first stream of the year, and I'm really excited for this. This is actually, we decided to, instead of doing just a normal stream where I talk about some stuff, we decided to make this a workshop of sorts. So we decided to have an interactive experience. Hopefully it goes pretty well. Now for those of you who are just joining in on YouTube or on Vimeo, this is going to be approximately a 1 hour event, and it's going to be an SSRF specific stream. I'm going to be talking about SSRF. I'm going to be talking about attack, and we're going to be talking about defense. And we have a few labs that we're going to cover around this area as well. Right. So let's talk about how this is going to work. Now, if you are an AppSec engineer subscriber, either a free subscriber or a paid subscriber, you have access to this for today, right? But the final version of the class, which is going to be uh, the version that is going to be on AppSec Engineer for posterity or whatever, not posterity, but at least which is going to be on AppSec Engineer as a final version. It's going to be available on AppSec Engineer probably in the first week of Feb, which is going to be the video edited, more labs, all of that stuff. That is only going to be available for AppSec Engineer subscribers, not for the free users or even the OWASP users. So if you're a corporate user of AppSec Engineer or somebody who's paying for a monthly membership or an annual membership, you have access to this class long term. But for today, you have access to the labs of this class on the AppSec Engineer platform. That's what I'll be using as well to be able to do the labs with all of you, right? So that's basically what we're going to be doing. So with that in mind, I'm going to get started. I'm not going to waste too much time. I'm going to start sharing my screen, and we are going to get started with this stream. I hope all of you are able to hear me on the stream. Somebody on Discord mentioned that we are waiting on the bridge. I don't know. I just joined maybe a minute late, so maybe that should have been addressed. Falconix, I'm not sure if you have access to that right now. If you, I think it is being streamed to the YouTube channel as well as the um, Discord, I mean, sorry, the Vimeo channel. So you should have access to it on both places. Anyway, so I'm going to get started with sharing my screen, and we're going to do a little bit of a slide stuff, and then of course we're going to jump into the labs. The labs are going to be the big piece, right? So let me just quickly start sharing my screen. Um, uh-oh, looks like I am going to have to change my browser. Just give me a second, please. Oh man, this is a bit of a pain. I was hoping that it would not be an issue, but nevertheless, I'm just going to have to move on. Just give me a second while I. Okay, I'm just gonna. All right, sorry about that. I think we are back online. Hopefully, everyone is able to see me now. I think we have some real-time views. I had to use Chrome mandatorily as the browser for this, so that's the reason why I was using Firefox. I didn't know that Vimeo has some weird issues with Firefox. Again, note to self: check that out before you start the stream. Anyway, so we're gonna start. I'm gonna start sharing my screen, and we are going to get started with this particular training, right? So let's get started with our SSRF Live workshop. First of all, very happy to be doing this. Now, so SSRF is something that I've been, my team and I, of course, it's not just me. Thanks to my team, we've been doing a lot of research in this area. In fact, we've found some new offensive security can do that as well. That may also be an approach of doing SSRF. But typically, you see the internal thing being the bigger target because internal is where the crown jewels are, right? That's where the data is. That's where the credentials are, and that's what I would want to compromise as an attacker. So if you look at SSRF, it's not very new. It's been around. In fact, the thing that gave this the most prominence, I think, in recent times was the Capital One breach on AWS, where they were able to compromise AWS credentials from that mod security firewall, and then they were able to access S3 and steal a whole bunch of customer data from S3. So that was pretty big. That was one of the big instances of this happening, and people really sat up and took notice of SSRF itself based on this. Right. Recently, we've had a whole bunch of SSRF flaws where this was the asset note SSRF on Jamf Pro Server, which is very interesting, where a profile URL field was used to manipulate Jamf, and they were able to compromise AWS, and they were able to gain access to internal resources and privilege escalate on their cloud environment and so on. In fact, even the proxy logon exchange exploit chain. So this was a huge exploit last year, and it gained a lot of prominence as a huge exchange exploit last year, and started off with SSRF as the key backbone of the attack chain, right? So if you're looking at it at SSRF, even if it's not the only way to do the attack, it's probably part of a chain that leads to the compromise. So SSRF leading to credential compromise, leading to privilege escalation, leading to what have you, right? So that's typically a very common feature of SSRF. So you see this happening quite a lot with SSRF and SSRF based workloads, SSRF based attacks and exploit vectors. Right. So SSRF can do a lot of things, right? You can do a lot of things with SSRF. I've mentioned a few things already: information disclosure, privilege escalation. So most of the SSRF payloads or SSRF objectives as an attacker, the SSRF objectives for me would be to escalate privileges, right? So I either read something or gain access to a system, or I compromise your cloud account. I do remote code execution. In fact, even be used for denial of service. Yesterday, I was reading about an SSRF attack where you would use SSRF to make bombard requests to an FTP server using the FTP protocol, and then cause that FTP server to essentially crash, right? So it can also be used for denial of service. In fact, you could use SSRF even to run a denial of service attack against other applications, even on HTTP, not only on FTP and so on. So there are lots of different variants and possibilities for SSRF, right? Remote file read. I've not mentioned local file read, but you can steal the etc password file if you have the ability to do that, if the SSRF attack or if the SSRF vulnerability allows you to do that. So not only does it allow you to read remote files and even do code execution based off of that, you can also do local file reads, local file includes, all of that stuff is possible with SSRF, right? So SSRF happens because the application makes HTTP requests, right? So your application might have a field like profile URL or social media URL or whatever it is that it needs to take from you as a user. And when you manipulate that, and instead of adding a genuine URL, you add a local host, whatever URL, or 169.254 or 169.254 or whatever it is, you should be able to gain access to the internal metadata or internal resources. So that's basically how that works, right? So it's HTTP requests. Application makes HTTP requests based on whatever is in the header. It could be also not only in the payload, it could also be in the header, right? So X forwarded for, or using some other header, HTTP header payload, you could be able to perform an SSRF. So it's not always in the payload. A lot of people assume that it's only in the payload or JSON request or something like that. That's not the case. It's also with a lot of these things that it could happen, right? So so this could be the first thing. The other thing again comes to the whole supply chain element of SSRF, where the library makes a request without you knowing it. So let's say you have some kind of a HTTP header processing library that makes a request based on a certain header it receives, or something like, Log4j is a completely different thing. But if you see what Log4j was doing, Log4j was basically just consuming the log entry, and it would actually run a command based on the JNDI interface and all of that stuff, right? So a library might be doing more than you think it does. So let's say there is some kind of a middleware that does caching or something like that might make a request to this.
If it sees a particular type of header, it might make a request without even you or your developers knowing about that request. So it's not always that your developers are making a mistake. There could be the library that could be making these unsolicited requests based on certain patterns that it sees either in the header or in the payload or whatever it is, right? So the attacker realizes, hey, you're using this particular caching product. I can add this particular header to this caching product, which will make this caching product automatically call some third-party URL, and that or an internal URL, and that would be something that they could control and compromise, right? So yeah, so this library or application basically content. Now the other thing, which is something that a lot of people tend to ignore with SSRF, is that a lot of content parsing libraries do this, right? So if you're parsing PDFs, or if you're parsing docx, or if you're parsing if you're converting images from one format to the other, all of these have headers and metadata capabilities where you can embed certain URI resources, right? And if you can do that when the parsing process, so let's say I have a web application that converts SVG to PNG, and that SVG to when they convert SVG to PNG, let's say your SVG is a malicious SVG that has things saying in the headers, it has something saying 169.254.169.254 slash metadata slash credential slash whatever. Then when that PNG is processed, that PNG comes back with the response with the whole metadata of that particular AWS server running it, or whatever it is in the backend. This has happened. In fact, there was this HackerOne report of TikTok, where I think it was TikTok, where the using so TikTok uses FFmpeg, which is a very popular video encoding library, and so they were able to manipulate TikTok's FFmpeg library, where they used the playlist files or a playlist reference file. Instead of giving a genuine playlist reference file, they used HTTP etc password or file etc password, and they were able to gain access to the etc password of TikTok's internal resource. So we're going to see something like that in our demo today as well. So that is something which is very interesting. So it's not only HTTP. You can actually use a whole bunch of protocols or schemes. So these are URI schemes, right? So you can use a whole bunch of schemes to be able to actually do this if your parser in the backend supports it. It's not always that this is guaranteed, right? Most of the time it's HTTP, but you do have certain parsers that supports file based schemes or Gopher or SSH or other schemes as well, even FTP, that kind of stuff as well. So you have parsers that are extremely wide scope parsers that can have that may be vulnerable because of this, right? So this is so yeah, so for me, the way I see it, the attack types is anything that you are URL parsing and consuming. This is typically what you see with a lot of SSRF attacks. You could have parsing or processing libraries that do PDF parsing or image parsing or video parsing or any other type of parsing that could have dynamic data embedded in the document that is to be parsed, right? So that is also going to be there. So that is something that you will see as well. And of course, you will see URI redirect capable. So SSRF, I think in the previous OWASP top 10s, I think this was 2014 or so, you would see an entry called Open URL Redirect. And that was basically kind of an SSRF itself, right? Because uh, it would redirect you to a particular URL, and that URL could be an internal URL or some sensitive URL or something like that, or a URL that is malicious, and that would also be an SSRF. So anything that allows this kind of open redirect or redirect to an internal resource, making requests to a protected internal resource, could be an SSRF attack possibility or attack type. Right now, you also have the ability to do this with DNS, in the sense so that when I say do this with DNS, you could a lot of these bypass and evasion payloads you could do with DNS, and I'm going to show you how that works in a little bit. So that's also a potential thing that you can use with SSRF. Right. So let's look at our first type of SSRF. I'm hoping that all of you are following in, and uh, is it is it working now? Sorry, Falcnix, all of you. There was a couple of seconds where it was offline, but I think it maybe. Uh, Not sure if it's. There are more people on the stream now, so I'm hoping that this situation has been resolved. Okay, super. I'm glad. Yeah, I'm sorry about that. That was a Chrome versus uh, YouTube thing. Um, Chrome versus Firefox thing. That was my bad. Oh, okay. You can't see a live video on YouTube. I'm sorry about that. I'll just put it up on YouTube afterwards. That is something that I might have to do. It's just a technical issue that I had to deal with. Anyway, so if you're on Vimeo, you should have access to it. Sorry about that. Anyway, so now let's do a lab on this. So for those of you who have a free trial account or a paid account, you should have access to this content already today. So I'm gonna just start sharing my screen again. Just give me a second while I open up on another browser, and I'm just going to start. Yeah. So all of you should be able to see my screen. So when you log into AppSecEngineer, if you have a free trial account, you should only see limited courses that are allowed for you. You should see a free tag next to it. But since I have a full AppSecEngineer access, you will see this course being made available. So server-side request forgery. Now I'm not going to be able to troubleshoot some issues if you that you might have during this process, because obviously we have very limited time, but you can reach out to us later on and we can probably help you out with something. So this is let's get started with the lab. So the first one is a HTTP client based SSRF, right? So this is an example that we built out recently, which was pretty powerful stuff. So actually I'm going to, so the way it works in AppSecEngineer, all you have to do is just click on provision and you get access to a live instance of the lab, which is dedicated to you, right? So that's how it works. And you can run 3 labs at a time at any given point in time. So you should be able to do that. All right, so just give me a second. I'm going to enable auth and then provision. Just give me, sorry about that. Now, those of you who are on the free trial account, you only have 2 hours of lab access. So please make sure that you use it carefully and quit as soon as you're done with the lab. Others, of course, if you have an AppSecEngineer subscription, you have unlimited lab access. You can use it however long you want. So I'm just going to reprovision it because I prefer using the authenticated mode, security and all. So uh, so I'm just going to start with this lab. Now, the lab is basically an application that allows you to enter some URL, right? So this application allows you to enter some URL, and that potentially leads to SSRF. So that is basically how this works. So you will see some examples of this, and the application comes back. So when it makes a request, so imagine that there's a social media application that it wants to link you to some avatar or profile or whatever it is. So this is that kind of a scenario, right? So let's actually run this lab. Now, the way I run the lab is I just open up a terminal and I pin it on top and I remove that other window there. So just easy. This works like Visual Studio Code if you're used to Visual Studio Code. So you just have to copy paste instructions. You don't have to do too much else. At least, well, if, of course, you can explore on your own time. You can look at the code and all that. But if you want to just run the lab and get an initial sense of what it's doing, you can just literally copy paste instructions. It's that simple, right? So this is a Python app that is using a very popular HTTP client for Python called URL-lib, right? URL-lib is a very popular HTTP client for Python. This is the standard HTTP client for Python. Literally hundreds of thousands of packages use this under the hood. So if you're making HTTP requests with Python, you are probably using URL-lib under the hood. That's basically what's happening, right? So URL-lib is a very popular one, and we're going to be using URL-lib and abusing the functionality to a certain extent. So we've built our Docker container. We're going to run the app now on port 5000. Okay. So we're going to be running the app on port 5000. The app is running. Now let's make a request. So we have so this is basically we had actually built this out as a full use case, and we'll probably in the final version of the course you'll see it with the UI and all that. But in this case, you'll see just the API. So this is an SEO optimizer. So the idea is that you give it a website and it makes a request to that website and sees what kind of SEO you have done on that website, right? So that's basically how it works. But obviously, the fundamental job of this particular variant or this particular application is to make that HTTP request, because that's the functionality, that's the feature. It is going to have to make requests to websites, uh, you know, third party websites all over the place. So I'm just going to make a get request to this we45.com URL, and you should see that it comes back with some data, right? This is normal, this is the feature, right? This is how it's supposed to work. So it comes back with a base64 encoded response from we45.com, and that's how it works. So it says that, hey, you know what, this is your URL that you gave me to optimize, and this is the response content from that URL. This is standard stuff. In fact, if you want to get a little bit more command line friendly with this, you can just do this, right? So you can essentially you can even decode the data, and you can do base64 decode, and it gives you the raw HTML content. So right now it came back with a base64 response, but if you want to decode it, you can do that with JQ and base64 and all of that stuff. Now, URL-lib, for those of you who are not familiar, supports the file scheme, right? It supports the file scheme, which means that I can do something like this. Instead of HTTPS, whatever genuine URL, I can do file colon slash 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 etc password, and it dumps the etc password, right? So this dumps the etc password because it allows the file scheme to be parsed, and I don't have any kind of validation against that. So I'm able to pretty much just dump the etc password from that remote machine. So imagine that this is an application running somewhere on the internet. I'm able to dump the etc password on from that remote machine on my response. So I'm able to get that response, and I'm able to compromise that application at that point. So I can even do file, let's say I want to do source code disclosure, right? So it could be file whatever is in the Docker file. So this is running in Docker. So this could be slash app.py. I can actually do that, right? So if I do /app/app.py, I think that should work too. So if you see what I'm doing here, I can even do a source code disclosure. So you can see that I was able to actually dump my application source code on this particular through SSRF, because my URL, you can see that the developer doesn't actually do anything. He's just making a request URL open. That's it, right? The developer does not realize at this point that there is URL lib supports the file scheme, right? It supports the file scheme, and because it supports the file scheme, it allows me to add file colon slash slash URL types, and it will parse whatever comes back from the file colon slash slash URL types unless you restrict it, right? So ideally, what you should be doing is checking the scheme, checking the domain, checking the path, doing validation. So input validation is your friend when you are doing when you want to prevent against SSRF, right? That's going to be the big deal. So if you want to do a great job of SSRF prevention, you want to do input validation extensively well. Of course, you can fix your parsers, you can do all of that stuff, but input validation is going to be a very important piece of solving SSRF as far as you're concerned, right? So this is going to be a pretty important thing that you will need to do when you want to address SSRF. So, right. So this is how URL lib works, right? So the URL lib based payload works like this. Now let's look at a slightly secure variant, which is also in the same lab, right? Now, if I try and access the secure variant, you should see that you should be able to read even the metadata. So even the metadata, it works with this because we're running it on the cloud, but we don't have any credentials mounted, so don't worry about that. So you'll see that it actually is able to access the metadata URLs uh, from my cloud server. It actually works. It's pretty dangerous stuff, right? So this works. Aside from the file, it also works with HTTP. I'm not validating anything in HTTP. That is a huge problem. So that is the issue. Now let's look at the slightly more secure variant, and let's quickly walk through what's happening here. So first of all, in the slightly more secure variant, it's not 100% secure by no means. Please, let's be real. right? It's not 100% secure, but let's look at what we're doing in the secure variant, right? So we're essentially using a different parser. We're using an HTTP client that's completely different. We're using requests, right? So we are using requests because in requests, you will see that request does not support file schemes and many of the other schemes that URL lib supports by default, right? The second thing we are doing is we have a block list, right? So we have a list of blocked URLs where we're not supposed to make these requests to. Now, this is not a comprehensive list. In fact, in another example that I'm going to show you later down with Go, you'll see that's a lot more comprehensive because it prevents access to any internal IP space. So IPv4 or IPv6, it prevents that. So that's not as comprehensive here, but it's definitely a lot more secure, right? So first of all, the file scheme is dealt with in this case. We're also dealing with these block lists, and we are also parsing the URL. Now, this is a very important thing. We're parsing the URL to ensure that the host name is not in these block lists. We can also do this to parse the scheme, right? So you can do URL parse, which is a parsing library in Python that parses the URL and gives you access to the scheme. And if the scheme is not HTTP or HTTPS, you can essentially throw it out, right? So that's basically how it works. So let's try using the secure variant to see whether this works. And so you'll see that it's an invalid URL because the secure variant, it is not going to parse. It's either it's in the host list, or if it's not in the host name, verify URL it's not a valid URL. So we are also using a valid URL validator. So this is a package that validates URLs, and file colon etc password is not a valid URL, so it fails the validation test. It fails the host name check, and it's both ways. It's gone. So it's obviously in this case it fails the verify URL test, so it says invalid URL, right? So if we try and do 169.254.169.254, that should also fail because it fails the block list, right? Our block list has 169.254.169.254. Again, this is not perfect. It should be better. It could be better. And you'll see an example where it is a lot better, just to give you an idea of how this works, right? So this is an example of the client-based HTTP client-based SSRF that happens. So file schemes are as susceptible as anything else to uh, you know to SSRF if you use the file scheme, or if your parser supports other schemes. Some parsers are super open-ended. Our clients are super open-ended. They give you access to all kinds of schemes. So that's one of the things that you should keep in mind, right? And that's something that we did, and we were able to address it in using a different client, using validating the URL, and you are parsing the URL and checking the host name. We've done all these three things, which is a good start. It could be made better, especially with the block list. We could have the entire private IPv4 range and private IPv6 ranges as well, and that would really solve the problem quite comprehensively in most ways. It still may be vulnerable to DNS rebind and stuff like that, but that's something we'll address a little bit later down the road. All right. So Falknick says it can be mitigated in IMDS v2. Yes, it is. That's for metadata only. But if it's, I'm talking about mitigating it as part of the application itself. Yes, it can be mitigated with IMDS v2. Absolutely. So that is the more secure metadata service that AWS offers, where you need to do a bunch of put and post requests. Put request first, get the token, and then do get request. So and that token is valid for a very limited time, and it needs an additional header or additional couple of headers as well. So yes, that is more infrastructure hardening, but this is more an app perspective. But yeah, you can do that as well if you want a restrict access to metadata, not for other things, of course. All right, let's move on to our next topic. Right. So the next one that I'm going to be covering is the parsers, right? So parsers are parser processor libraries are pretty big, and we're going to be talking about that and seeing how they can potentially cause all kinds of issues with SSRF. SSRF can have all kinds of impacts with this. So just let's share my slides. Share screen. share window, and here we go. Right. So one of the things that I was mentioning before was the use of these PDF generators and other processing libraries. So PDF generators are extremely one of the things that have become pretty a heavy target of SSRF attacks because they have a lot of functionality. So PDF generators typically take HTML content and then use either a browser or they use an HTML kit to render it to PDF, right? So that's how they do it. So, which means that you have the full scope of using HTML to be able to do this. And that's the dangerous part with PDF generator libraries. In the sense that you can, since you have the ability to use source tags in HTML, you can use image source, iframe source, style source, link source, whatever source, and you should be able to perform SSRF because it'll make a request to that resource and use that as the source when it's embedding in that particular document. So this is a really interesting type of attack vector that we've seen, especially with PDF generator libraries. This was initially discovered, I think, by Nahamsek and Cody Brocious. This was a very interesting. I saw the talk; it was really interesting the way they had gone about doing their research. It was really good. So this was a PDF library called WeasyPrint. Now, WeasyPrint is a very popular PDF generator processor library. So you essentially give it HTML, it converts that to PDF, and you can use that to generate reports. You can use that to generate whatever you want in PDF, right? So WeasyPrint allows you to use the link tag. So if you don't validate what is going into your HTML that is being processed finally as a PDF, then it could be very dangerous because somebody could embed a link tag in there, and that link tag could have they could source that link tag to HC password or 169.254 or some other third party URL and cause all kinds of security issues, right? So this is our next lab is going to be a walkthrough of our lab on WeasyPrint. So I'm going to just share my screen and we should be able to get started with that. So yeah, that is WeasyPrint. I'm just going to quit this. And let's access the WeasyPrint lab. So I'm just going to provision my box and we should be able to get started in a couple of minutes. We have about 20 minutes or so more. And I'm just going to go over some of this stuff. Again, this is not the final class for those of you who are on AppSecEngineer. This is going to be, of course, we're going to be re-recording all of the videos, and the labs are going to be a little bit more optimized as well. This is just a class that we're doing for the community. So just waiting for the lab to provision. And once it does, we should be able to get started with WeasyPrint. So this example is one where we have a CRM style application. And the CRM style application is basically just an application where I can sign up and I can enter some customer details and I can get a PDF export of my customer details or whatever, right? So let's look at how that goes. So I'm going to spin up my application first. And this is me spinning up the application. So this is a Python app. I have Python and Go examples. We did have a couple of Node examples as well, but they were kind of the same things. So we wanted to showcase some of the more unique ones. So that's why we're doing it. But we have a Go one at the end as well. But yeah, most of them are Python. We have some Node and we have some Go as well. So let's access this application on port 5000. So that would be this. Right. So here I have a standard application where I can sign up, right? So I say, hi, last name Bhargav, abhay@test.com is my email, and I set a super strong password. And instead of remarks, so this is like a open field, instead of remarks, I am going to add a slightly malicious payload. I'm going to say link rel attachment etc password, href file // etc password. I'm going to sign up. Okay, so it's going to be abhay@test.com and it's going to be this. right? So now I'm going to generate my PDF. Okay. So once I generate my PDF, it actually just looks like a normal PDF. It has nothing. It just has my information. If I had entered some customer information, that would have been printed here too. But in this case, it's not, right? So I'm going to essentially download this file and I'm going to upload it back to my machine. So in fact, I don't think I need to do that, but oh yeah, it's actually generated on the back end as well. So I don't need to upload it. I'll just do it from here. I don't need to re-upload it. Now, this file, this PDF file just looks like a normal PDF file. It doesn't have any etc password and all that stuff. But the idea here is that we use link rel attachment, right? So we used it as an attachment. So it means that it could be potentially embedded in this file. So let's look at this file and let's actually break this file down and see whether it's actually done that. Okay. So I'm going to access that is WeasyPrint app static, and here I have my file. I'm going to use binwalk, which is a binary binary that essentially allows you to examine binary formats like PDF or many other formats. Is pretty much used in a lot of forensic use cases, but in this case, we're just going to expand our PDF file and see what's in the PDF file, right? So I'm going to binwalk this, and it says it's a PDF, and it decompresses it, and it removes all the compression, breaks it down into a whole bunch of zlib files, right? So if you see this, you just walk through some of the zlib files. It just gives you some PDF metadata stuff. It gives you some data related to the file. You'll see that this is pretty standard PDF stuff, but somewhere down the line, you should see some interesting stuff where you should see the etc password, right? So this has successfully retrieved our etc password. So if the attacker downloads that PDF file, which is a pretty standard PDF file, and runs binwalk, because of that link attachment, the attachment has been able to pull in that etc password or any other URL that I'd given it, and I'm able to use that as an attachment uh, in the PDF file. So it doesn't show up on the face of the PDF file, but because it is an attachment, it is attached to that PDF file. Very much like a mail attachment. It doesn't show up on the mail itself, but it's a separate entity that is embedded. Now, this is very similar to that example, right? So that is how this works. So WeasyPrint and a lot of these, this is not only WeasyPrint, right? You see this with ImageMagick, you see this with FFmpeg. I told you about the TikTok example as well, where a lot of these parsers, a lot of these formats allow you to embed or allow you to add certain metadata parameters to that because you need it for header validation or you may need it for some identification or whatever it is. So SVGs, for instance, if you're using a library called ImageMagick, which is an image processing libraries, and if you're converting SVGs, it allows you to embed some metadata information in the SVG, and it could be a URL, and that would when a vulnerable version of ImageMagick is used, it actually allows you to pull that URL uh, into the final file format that gets converted, and that also causes SSRF. So literally, all of these parser libraries have a massive impact for SSRF because you might be using a vulnerable version or you might be using vulnerable configurations of these parser libraries, and that causes a whole bunch of security issues as well. Right. So this is one of those classic examples of how things can go horribly wrong the with SSRF. So it's not always that developers are making the mistake. It's a lot of times because these parsers have a natural thing. So they might have configuration parameters that you need to set, or you might have to patch them. Or in the case of WeasyPrint has nothing. You have to essentially do validation to ensure that whatever HTML you don't want doesn't get into that WeasyPrint conversion process. Otherwise, it will just make that response, especially link tags. Will just make that request and get that response, right? So this is very common with a lot of these parser libraries. You see this with ImageMagick, you see this with FFmpeg, you see because FFmpeg allows you to embed playlist files when you are converting videos, and it will essentially use that to convert a bunch of videos into whatever different formats. It might change the format or it might compress the video, whatever it is. So that's basically how that works, right? So that is one of the things that you will see with with SSRF. So I'm kind of running late, so I'm going to move on to defense because I don't want to. There is an XML example as well, which is a very interesting example, but I don't have the time to cover it. It's quite a large example, so I'm going to move on so that we keep to the 1 hour slot, and then I can give you an example of the Go and the defense and some of the defense parameters as well. Now, the other example of what I'm going to be talking about is DNS bypass, right? Now, DNS, imagine that I have a URL. So let's say the attacker controls a URL called blog.sometld, right? Now, blog.sometld, it does not necessarily resolve to an external IP address, right? The attacker might have set up the DNS in a way that it resolves to an internal IP address. So let me tell you what I'm talking about. So let's take an example of what I am mentioning, and I'll just show you as well what I'm talking about here. So just give me a second while I set it up. Um, I'm just going to do a little bit of a live code example here, so you'll see what I'm talking about. All right. So I'm just going to start sharing my screen. All right. I'm guessing everybody can see my screen. I'm just using Visual Studio Code to write something as a real world example and show you how that works. Okay, so let's take, so one of the things that happens with DNS rebinding is that instead of so let's say you have a block list and you say that, hey, I don't allow the my library to access. Am I back? Uh, is it working again? Hi everyone, is this working? Sorry about that. I think there's something wrong with. Yeah, okay, great. Okay, great. Sorry about that. This is just. I don't know why Vimeo is being difficult today. I should have just used StreamYard. And are you able to see my screen? Are you able to see my screen now? I've just opened up my entire screen. So hopefully, I used to share windows, but now, yeah, okay, great. You're able to see my screen too. So you see what we're doing here is I have locally.cwdetails.com, but if I use a block list, it still doesn't work. So let's look at this as an example, right? So let's call this block url.py. And I'm just going to quickly write up. So I'm going to do import requests and I'm going to say block URLs is equal to 127.0.0.1 localhost and 169.254.169.254. Okay. Now, I'm just going to run another small program here. Just give me a second while I do Python http.server. Right. So this is running on port 8000. Now, if I do this, so if I do something like this and I say request if, so I do from URL lib.parse import URL parse, right? So I'm just going to parse the URL and do pretty much the same thing, right? So let's take my URL. I'm going to say http locally dot cwedetails.com colon 8000, right? So this is my URL. Now I'm going to make if, so I'm going to parse this URL. So I'm going to say parsed is equal to URL parse of URL dot hostname. If hostname, if parsed, uh, not in blocked URLs, then requests request dot get URL, else print I can't make that request. So now technically, if I parse this, so let's say I run this, right? So if I run this code, which is here, sorry, block URL. So let's take another example. So let's remove this and take a simpler example. It should block it, right? So I'll say HTTP localhost colon 8000. So this won't work. I can't make that request, obviously, because it is in the blocked URLs. I'm not going to be able to make that request. It says localhost, very clear. It's not going to be able to make that request. So I am still, I am potentially protected against SSRF, right? Not really, because if I load up a domain that points to, so if you see locally, what locally resolves to, so if you see locally dot cwedetails.com resolves to, you will see that it resolves to 127.0.0.1, which is strange, right? So now when I do this, it still makes that request. It makes that request, and if I'll just print out the r.status code, and you should see that it works. It works just fine because while I've set up a host name block list and I'm making it on the HTTP client, my DNS resolution is not linked to this, right? It's a completely different ballgame. It resolves to that on my DNS, and as a result, it's still going to work, and I can still do SSRF, right? I can still perform my SSRF attack simply because it resolves to the DNS. So because of the DNS resolution thing, I am able to make this request and my SSRF works just fine. So there are ways out of this. I mean, there are DNS proxies that you can use before resolution. You can use eBPF perhaps. You can even rewrite firewall rules to not have access to local host and stuff like that, which is a little harder to do. But there are ways out of this, but it's a little harder than typical URL parsing functionality that you are typically used to, right? That is the big difference between this and the standard HTTP requests and response type of checks that you're doing here. This is blocking a host based on what it sees as the host. But under the hood, it's going to resolve back to the same host. And that's what I'm talking about with DNS rebind, right? So that is basically what the issue is with DNS rebind, and it can be pretty bad. It's a lot more complicated to deal with this because you need to have DNS proxies. You can probably have a DNS provider that does not resolve external to this. So, for instance, OpenDNS, for instance, does not resolve external domains to a local or a protected domain, protected IP address space. So that is something you can do if you have that. Some cases, if you don't have that, you might have to add a DNS proxy or some kind of a thing, or some other kernel level, network level control to be able to prevent that sort of DNS resolution from happening. So you might have to hook into the DNS resolve process and then say block this if it is one of these IPs, which is a local IP, and so on and so forth. So this is the kind of stuff that can get pretty dangerous with DNS rebind, right? So this is an example of DNS rebind. So if you look at the defense, let's talk a little bit about the defense that we're looking at. And I do have one example that I'm going to end with today. So if you look at DNS, if you look at the defense, you will see that you have different varieties of defense that you can do. So for instance, let's say, it really depends on the feature that you're dealing with. So let's say your application has to resolve external URLs, right? So let's say it's a profile URL or LinkedIn or whatever it is. There, you might have to resolve external URLs. You might have to make a request to external URLs. There, what you can do is prevent access to the internal space, right? So local IP addresses or internal IPv4, IPv6 IP addresses. You should not, essentially, they should not have access to that, right? So you do not have to allow that. If you have a functionality where you can restrict the URLs to a very specific set of hosts, that's great. That's probably the best, right? That's probably the best. But if you can't, then you might have to add firewall rules on the local host, and that might be a little harder to do, but you might have to do that. You might have to rewrite your HTTP client to not make requests to this. You might have to rewrite. In fact, that's what I've done in the Go example that I'm going to show you now. So you definitely have to, input validation is the biggest thing that I think you need to do, because you need to validate the scheme, you need to validate the port, you need to validate the host, you might need to validate even and this has to happen wherever you're processing URIs. And of course, if you're using libraries that are vulnerable to SSRF, that is a whole different story. You might have to obviously check them constantly for security issues, and then you have to patch them or change them out or do whatever you need to with them, right? So this is something that you will need to do. Network security is an option. So if you can use firewall egress rules to be able to prevent access to internal IP space on non-standard ports or whatever it is, that may be something that you want to do. That is also a possibility, but again, it really depends. Sometimes it may not be possible for you to prevent access to the local host or the internal IP space. You may not be able to do that. So you might have to add more application-centric controls in that particular case. Now, in terms of infrastructure, especially metadata access like AWS and stuff, AWS today has the option of doing IMDS v2, right? So this is the instance metadata service version 2, where if you add this, it automatically does not allow just a standard GET request to make a call to the metadata and gain access to the credentials and all of that stuff. That is definitely a good thing. The other cloud providers automatically do this. So they have the ability to, you need to add additional headers if you want to make a call to the credentialed metadata service. So that is something that you have with other providers like Azure or GCP. But with AWS, you have to use IMDS v2 to be able to prevent SSRF against the accessing the metadata service, right? So that is basically what you need to do. Now, for our last example, I'm going to be looking at a slightly different example, and I'm going to showcase this. This is something I wrote just a week ago. This is an interesting example because I use a slightly different approach to to fix the SSRF flaw in this case. So let's provision that instance. Just give me a second. All right. Looks like what? Weird. Is it provisioned or not? Okay, it is. So this is an application which is a very simple Go web application, right? It's very simple Go web application, and it just essentially you give it a name and a URL. It will make a request to that URL and come back with the response. That's basically what it does. Now, the idea here is to add a lot of defense to this, and I'll explain the defense element once I run this, right? So I'm just going to quickly run this app and show you how it works. It's a very simple app. Just you need to provide it a name and a URL, and it will go and fetch that, come back with a response. That's how this works. So this is backed by a CouchDB database. So there's a CouchDB database in the backend. CouchDB is a very popular NoSQL database that you can access directly on HTTP, right? So you can access it like a web service. So that's how it works. So we are setting up a small CouchDB instance, and we're going to access that CouchDB instance. So I'm going to build my SSRF app, and once I do that, we should be able to start interacting with my Go application. This does take a little bit of time. Go has to compile all the dependencies, and once that's done, you should see that it starts to work pretty quickly. Yeah, so it's just compiling, building all the dependencies, and once it's done, you should see that it's done. Yeah, so we're done. We're off to the races. We're going to be running on port 8080, right? So now if I make a request to this, right? So I just need to provide a name and a URL. I just change this to get, not post. So when I do that, it just comes back with the content. So if I want to see what's the actual content, You'll see that this is the content. This is an external site which is valid. This is the valid functionality for this particular application. This is an external site that I am accessing. Now I can also obviously do this with the internal URL. So if I do with the so let's say I know that there is a CouchDB in the backend, I can access this and say, get me all docs of the CouchDB. So if I want to do this and see what are the docs of the CouchDB, I just base64 dash dash d code. I think I'll change the instructions after the class. So you'll see I'm able to fetch the database entries of CouchDB from the backend. So this is a classic SSRF attack, right? So I'm able to do this. Luckily, Go's HTTP client does not allow other schemes like file and all of that stuff. You can't do that. You can only use HTTP with Go's HTTP client. So that's one less headache that we need to deal with. Unlike URL where it supports file schemes as well. So here I can even do, of course, the DNS rebind variant. You'll see that I'm able to access this as well, right? So now what I did was I rewrote the HTTP client itself. So I rewrote the HTTP client, and I'll show you what I did for that. So basically what I did was that in Go, the HTTP client, you can rewrite something called a transport, right? The transport essentially is what kind of HTTP configuration you should have. What is it has something called dialer, which actually makes the request and sets the transport and all of that stuff. So here I've written something called a safe dialer, and I've written a secure socket. So I've checked whether it's TCP4, TCP6. I'm going to split the host port and check whether it is a valid IP address, and I'll check whether it's not a public IP address. This is a big thing, right? So whenever I'm making a request, every single time it will check whether it's not a public IP address, and I've written a function to check whether it's not a public IP address. It'll check whether the port is either 80 or 443, and only then the HTTP client itself will not make the request. So I don't have to set up any external block lists and all of that stuff. My HTTP client library itself is a lot more hardened than normal as than the normal HTTP client, right? So this is basically I've set up something called a safe transport, and I've done that, right? So if you see the network stack, you'll see that I have done IPv4 check. It checks for whether it's an IPv4 a list of reserved IPv4 network addresses, IPv6 network addresses. Then it comes back with, is it a public IP or not? So it checks all of these different ranges, and then so this is a lot more robust than my previous solution, right? In this case, it checks all of these potential IP ranges, and then it comes back with whether it is a valid IP address, valid public IP address or not. And if it's not, it will not even make the request, right? So let's do that. Let's actually rerun this. Let's rebuild the container and rerun this. I'm just going to rebuild it. Yeah, so it's going to rebuild the thing. I'm going to remove the running container images. And now we are going to run Docker. All right, so we're running, and let's actually go ahead and see whether our attacks work. So you'll see that I've actually explained all of this stuff against it, right? So locally addressable IP addresses, non-HTTP, all of that stuff has been done. So I am going to try and run it against the external site, and it just should work just fine because it's an external site. It clearly resolves to an external IP address. It works just fine. So you'll see that it works just fine. But now, if I try and resolve it to my local host, you should see that the client itself does not make the call, right? So it's kind of like rewriting or creating a secure default client library, right? And that's one of the things that I like about this approach, because you can just distribute this variant of the library to all your developers, and they don't need to think about SSRF to a large extent. Excuse me, unless there's something new that you need to add to it. And of course, you can always update this library at that point in time. I like this approach the best because it is the most scalable, most easy to scale, easy to use approach for all your developers. So a couple of people or a small group can work on this, make sure it's robust, test it out correctly, and then give it to everybody so that it actually solves it at a supply chain level. Right? That's something that you can do as well. So with DNS rebind, of course, the port should. I'm not sure whether this doesn't work against DNS rebind, but definitely because the port restriction, it should not show up because again, either 80 or 443 is allowed, everything else is completely not allowed. So that is basically the approach we are using here, right? That's basically how we are doing this. So that's the example that we had. That brings us to the end of our stream. Now those of you, thank you for staying and watching. Yeah, it does resolve. Local test, this resolves to local host. I think, yeah, I need to put a DNS proxy. This is not going to solve it at the HTTP client level. It's either a DNS proxy that I need to put in, or I need to put in some kind of a network security rule. So network security or DNS proxy are the two ways out. Simply because this was a different port, it didn't work. I need to change that DNS rebind, that it fixes the DNS rebind. It does not fix the DNS rebind. That's something I thought it wouldn't, but I was not sure. But anyway, yeah, it shouldn't. You need to do you need to put in a DNS centric solution for that, for this to work. Anyway, that brings us to the end of our stream. Thank you so much for watching, and I'm sorry to disappoint our YouTube folks. If this has not been streaming on YouTube, I will put it up on YouTube just to make sure that you have access to it on YouTube as well. So that's really it from me. For those of you who are interested, you should sign up for AppSecEngineer. You will have access to all of these classes or more, and you will also have access to a lot of other material that we're releasing, which is a lot of fun. Please stay connected to our Discord community. It's a lot of fun. You have a lot of interesting conversations on there. So yeah, that is something that you should definitely consider doing. Thank you very much. Stay safe, and I'll see you in another workshop or another event. We're planning to do this on a monthly basis. Now, for those of you, for all of you, this labs will be available for the next 24 hours. It will be shut off tomorrow. But for subscribing AppSec Engineer users, you will have access to the full class come February 1st week. So you should have the full class come February 1st week, along with all the labs and the videos and the slides and all of that content. Right. So you will see a lot more content from this space. Thank you very much. Appreciate it. And thank you very much for the Discord community as well. Appreciate you staying and, of course, bearing through those small technical glitches that we had. Appreciate it. And look forward to seeing you in another event. Thank you. Yeah, we are doing it monthly, by the way. Yeah.